Okay, so what I decided to do is I get a choice on how I'm going to start. I'm going to initialize the pendulum. So I decided I'm going to initialize it with the vertical position as the 0 position, which means that now I can draw the links from the vertically downward position. So I'm going to draw them like so at some angle. It's link 1, link 2. And that dot is basically indicating the pin joint. Now, as I said, the angles are going to be with respect to the vertically downward direction, that's theta 1. And you have a choice. You could also have theta 1 to be the angle between the vertical and the pendulum. It's totally up to you. We don't have a choice on the second angle. It's basically this way. It's the angle between the line extended from the first link to the second link. Okay, let's draw the center of mass. G1 and G2. And let's say that this one is at a distance of C1 from the pin joint, and the other one is at, say, G2 is at C2. And we only need the length of one of those links. So, I mean, other one is not important here. It may be important in the Jacobian, but not here. So we just need this length. That's L. And let's say that the pendulum has a mass M, well, M1 for the first link. Inertia I1. Second one, it's going to be M2, I2. Okay. Now that we have that, that would be your problem description. You need to derive the equations with those things given to you. So the way we'll do this is we'll assign coordinate frames. So by default, this is the horizontal is X, the vertical is Y. So we'll start at assigning frames. So let's do with this. X0, Y0, that particular frame is fixed. It doesn't change. It's the fixed frame. The origin associated with that is O. Okay, now let's draw a frame for the first link. So that would be, again, that's a choice you can make. So here I'm just making a choice which is X1 is along link 1 and Y1 is normal to that. So this is X1, Y1, and then second one is like so, X2, Y2. The origin is O1, and this one origin is O2. Yeah, then I forgot to draw gravity. Gravity is pointing downwards. Yeah, so we'll follow those 3-4 steps we talked about. First is we need to figure out the position of the center of mass. In this case, there are 2 center of masses, and this should be in frame X0, OO, XO, YO. That's the base frame or fixed frame. Okay, so if you remember, if you want to find the position of the center of mass, so that will be G1. in frame 0. That would be the homogeneous transform relating frame 1 to 0 times G1 in frame 1. And in this case, H10 is basically a formula. It's R10, O10, 0, 1. And we can expand that out. R10 is cosine of the angle made by frame 1 with respect to frame 0. So, see. So essentially, it's the angle made between x0 and x1. Okay. Now, you can see that one way of computing that angle is going clockwise like this. Another way is to go counterclockwise. Okay. I would say that you should always stick to the counterclockwise convention. It makes your life easy. You could go clockwise, but then there are complications like clockwise is negative, and then you're always confused about signs and so on. So just do the simple thing, go counterclockwise, which is a positive direction. So in this case, we do sweep from here all the way there. I'll just draw that separately because the figure is cluttered. All I need is x0, x1. This is theta 1. And I need to go counterclockwise. So I'll just do that with a different color. So I need to go 90 degrees, then another 90 degrees, another 90 degrees, and then there's be theta 1. So that's 90, 90, 90, and theta 1. So it's 90 plus 90 plus 90 plus theta 1, which will be 270 degrees plus theta 1. So that's my angles, which I put down in this equation for H10. So cosine of 270 plus theta 1 minus sine 270 plus theta 1 sine 270 plus theta 1 cosine 270 plus theta 1 0, 0. And then that would be R10. O10 is the position of origin of frame 1 with respect to frame 0. But remember that what's happening here with this frame 1, is that it's only rotating, it's not translating. So that position is simply 0, 0, x and y, and then this one. So let me put it this way. So now we can relate. This part is here. This part is this, and so on. So I have computed H10. The next I need to get is G1 in frame 1. So G1, position of G in frame 1. So for that, you only need to take a look at frame x1, y1. You need to find the coordinates of G1 in local frame x1, y1. So you can see that G1 is along x1. So the coordinates of G1 in frame x1 would be simply C1. The y coordinate is 0 because it's not along it's only along the x-axis. So G11 is going to be C1, the x coordinate, 0, and then this 1 is a placeholder. So this one just make computations possible. It turns out that if you do this math, that is put these down and do the matrix multiplication, you get C1 sine theta 1 minus C1 cosine theta 1 and 1. Okay, let's do the same thing for G2. G2 is here. So G2 in frame 0 is H2 in frame 0 times G2 in frame 2. Now H2 0 is H2 1, H1 0, G2 2. So we have already computed H1 0 in the previous, in the previous page. H2 1 is R2 1, O2 1, 0 1. Okay, it's R2 1. If you want to compute that, it's basically the angle between X1 axis and X2 axis. X1 is here. It's basically this. X2 is here. So the angle is theta 2. So all I need to do is use theta 2 in my formula. Cosine theta 2 minus sine theta 2 0. Okay, so that's R21. Next, I need to compute O21. Let's see what that is in the figure. Okay, O21, this is O2. We need to compute the location of O2 in frame 1, this frame. Okay, you can see that O2 is along the X1 axis. So its location is going to be L along the X-axis. So we take that and put it here, L 0 because it's along the X-axis, 1. Okay, the last thing left is to compute G2 in frame 2. So again, go back. We have G2 and G2 in frame 2. So it will be in this frame. So it's so since G2 is along the X2 axis, its location is C2 along the frame in frame 2. So G22 is C2 0 and 1. Along X2 distance along Y2, and then this is just a placeholder. Okay, so what's left now is to compute G2 in frame 0. Okay, so H10 is known, H21 is known, it's right here. G22 is known, so you can either do it by hand or by using symbolic toolbox. G20 comes out to be L sine theta 1 plus C2 sine theta 1 plus theta 2 minus L cosine theta 1 minus C2 cosine theta 1 plus theta 2, and then this 1 is a placeholder. So okay, so we've computed the position. In order to find the Lagrangian, we need to compute the velocity. So let's do the computation of the velocities. So we need velocity of g1 in frame 0. For that, we need to do the derivative of g1 in frame 0 with respect to frame 0. So we already have that. So it will be d dt of, and I'm going to ignore the third quantity, but this comes right from here, from the first page. We have computed this. So I'm just going to substitute this formula there. C1 cosine theta, C1 sine theta, should be minus C1, sorry, it should be C1 sine theta 1 minus C1 cosine theta 1. So the derivative comes out to be C1 cosine theta 1 minus C1. So minus of minus is positives. I forgot something here. Theta 1 dot, right? So it's derivative of theta 1 with respect to time. And then we have C1, derivative of cosine is negative sign. So sine theta 1 times theta 1 dot. Similarly, we need to compute VG2. That'll be G2 dot 0. So d dt of the long expression I wrote down sometime back. It's L sine theta 1 plus C2 sine theta 1 plus theta 2 L cosine theta 1 minus C2 cosine theta 1 plus theta 2. And then when you carry out this differentiation with respect to time, you end up getting C2 cosine theta 1 plus theta 2 cosine theta 1 dot plus C2 cosine theta 1 plus theta 2 dot, and then C1 plus C2 sine theta 1 plus theta 2. Okay, so you see that's getting it's kind of lengthy. We also know that theta 1 dot is omega 1. That's the angular speed, just a different notation for the angular speed. You could use either of those. Okay, that's step 2. We've computed the velocity and the position of the center of mass. Now we go for the total energy. That's going to be half m Vg1 square plus half m1 Vg1 square Vg2 square plus half I1 theta 1 dot square. Okay, and then for the other one, so that's the angular velocity of link 1, but the angular velocity of link 2 is going to be theta 1 dot plus theta 2 dot square. Okay, I'll tell you why that's true, why that's so. Okay, so the angle made by the first link with the vertical is θ1. So the rate of change of its speed with respect to the world frame 0 is going to be the rate of change of θ1. The angle made by the link 2 with the world frame is actually θ1 plus θ2. So its angular speed is going to be the rate of change of the absolute angle. So θ1 plus θ2 squares. That's why it is this. Okay, now what you need to do in order to get this is this is going to be this square plus this square, right? So it's going to be C1 cosine θ1 dot square plus C1 sine θ1 dot square. So that's going to be velocity of g1 square. It's going to be the x component, and then the y component. Okay, so that may not be too bad. Now let's, if you want to do this for VG2, you need to take this whole thing, square it, and this whole thing, square it, and then sum it up. Now that's getting much harder, right? I wouldn't even try to write that, but you will have to take, if you write this as, let's call that VG2 VG2x maybe, or sorry, y. And then if you call this VG2x, this thing would be VG2x square plus VG2y square. And then that just is so messy. It's going to be very lengthy. And then once you get that, the remaining terms are not hard, but that term itself is going to be pretty long, and I can show you the length of it when I show you the code. Then we have the kinetic energy. That's going to be, that's kind of straightforward. M1G G10 plus M2G YG20. So these come from the position, the y position of G1 and G2. So that would be the y position. If you go back to the position, it's going to be, this is YG2, and then this is going to be YG1. We should just write it down. Minus C1 cosine θ1, and YG2 is minus L cosine θ1 minus C2 cosine θ1 plus θ2. Okay, so what we've achieved here is we have computed T, we have computed V. Okay, T is the kinetic energy, V is the potential energy, and now we need to compute the Lagrangian, which is just the sum or the subtraction of the two. So L is T minus V. It's going to be some vague expression, which I will not even try to write down because it's going to take a couple of pages. The third step, which is more of a plug and chuck, is to use the Euler-Lagrange equations. So that would be d dt dl dq dot j minus dl dq j equals qj, where small qj will be, well, it will be the degrees of freedom. In this case, you need two angles to describe the motion of the pendulum, θ1 and θ2. So you'll end up with two equations. Here it turns out that there are no external forces, so Qj will be 0 for both degrees of freedom. So use that to compute the two equations. Yeah, I'll show you this and then we'll go for the next part of animation. I have some cookies from an event which we had on Saturday. This is sponsored by the mechanical industrial engineering. You can pick one and then just pass it on. The double pendulum equations in Python. So define symbolic variations, and I'm trying to make it so that it looks similar to my derivation. So for example, I have said here in the comments 1a get the position vector. So you see that the equations here sort of are similar to the ones I have on the notes. So for example, 3, if you remember, 270 degrees is 3 pi divided by 2. So h01, h12, c1, this should actually have been, okay, I can change it later on. Xg1, yg1 is the positions of the center of mass. I get the velocities, vg1, xy, vg2, xy. I compute the Lagrangian L, and then I do derivations. So this is basically copy paste. Once you have q dot set up, it's basically generates the equations for you. Okay, and I'll talk a little bit how the equations generated, but let me show you something before that. This is going to print nothing by default. It's just going to derive the equations. So maybe, sorry, it'll print the last lines, but let me just try to make it print the print L. Okay, so it printed L, and let me see what L looks like. This is L. This is this piece. Not so much. It stops here. Okay, so this is what L looks like. Okay, so it's fairly complicated. Now it gets more messier if you do more links, but you don't want to derive this by hand. Okay, so let me show a little bit more, and then I'll show you animation, animation of the double pendulum. There's a certain way in which these equations are written down, which makes our life easy, and that's what I wanted to indicate next. Okay, so I've shown you the I wrote down this equation. Now it turns out when you write these equations, you are going to end up getting two equations. Okay, the first equation will look something like this. Okay, so you'll see that there's acceleration, theta1 double dot, theta2 double dot, and they will be a11, a12, which of course will be functions of theta, mass, c, and so on. Then there'll be another equation, a1, a21, theta1 double dot plus a22, theta2 double dot equals b2. So you'll end up, of course, A's, B's are functions of M, C, G, L, and I. So what you'll do is you'll write this as A theta double dot equals B, where A is A11, A12, A21, A22, theta1 double dot, theta2 double dot equals B1, B2. And then you will invoke, you'll basically solve for theta double dot as A inverse B. Now you could do this A inverse, you will get this A matrix in Python. It will be fairly small, but if you try to do A inverse, it starts becoming kind of humongous. And so you want to avoid inverting matrices symbolically. So when we do this, we'll actually keep track of A symbolically, but to compute A inverse, we'll put in the values in the simulation compute A as a matrix 2 by 2. You'll have only numbers, and it's much easier to invert a matrix with numeric values than to invert a symbolic expression. So what I do here is in the code, runtime, yeah. So what I do in the code is, we comment this. So in the code, I extract the A matrix. So M is the same as A in the notes. And then I basically also get C1 and G1. I've written down because in that fashion is because that's how you'll see in books. But that is basically B1, and then C2 plus G2 is B2. So the code here extracts these things from their equations, and the way it is done is kind of interesting. So, and I learned it from somewhere else. So the way you extract the terms is in this equation is you'll put, for example, you'll put theta1 double dot and theta2 double dot equals 0 in the symbolic expression, and what remains will be B1. So you got B1. Then you'll put theta1 double dot equals 1, theta2 double dot equals 0, and then you'll get A11 plus B1, but you know what B1 is, so you subtract out. So it's like just manipulating a symbolic expression by substituting the values, which is done right here. So here's one of them, which is putting 0, 0. And then actually, I don't use that trick. I actually use the Jacobian. So if you do the Jacobian of the equations with respect to alpha 1, alpha 2, theta 1 double dot, theta, you actually get the M or A matrix out. Okay, so once that is done, once these equations are out, M11, so on, it goes in this file, M. This is the simulation of the whole thing. I have the equations right here. So it was copy pasted here, double pendulum, you have M11, M12, and so on. And then you can see that I actually invert. I could create the A matrix from M. I have the B matrix, which is C1 plus D1, the same thing I wrote down. I invert A, I get B. And then once I multiply A inverse times B, the first thing in theta double dot is basically alpha 1, alpha 2, or the acceleration, which then goes in dz dt. So I'm going to run this animation, simulation animation. So it does the same simulation as you saw in Coppelia Sim. This time, all the equations were hand derived. Okay, it's fairly short code, about 170 lines, a bunch of almost half of that is, I believe, is the animation routine, which is plot here, right from 58 all the way to 100. So about a fourth of it is just animation. Okay, so mass, angles. I also keep track of energy. So one way of checking if a system, if your equations is right, you're doing right, is to look at the total energy of the system. If the energy is constant, then the system is your simulations are correct, because a system with no dissipation will show that energy doesn't increase or decrease with time. So that's check I do, but you don't really need that unless you're checking the equations.